Okay, let's start our today's seminar. Our speaker is Professor Péter Rucz. He graduated as an electrical engineer at the Budapest University of Technology and Economics in 2009. He received his PhD degree at the same institute in 2016. Péter is currently an associate professor at the Laboratory of Acoustics at Budapest University. His research focuses on the physical modeling of musical instruments by means of numerical techniques. His interests include IRA and vibroacoustics, numerical methods, and signal processing. And today, his talk is dedicated to the computational models of weakly nonlinear sound propagation in ducts. So, Professor Rucz, the stage is yours.
Yeah, thank you very much, and thank you for the kind invitation and also for organizing this online seminar. It is my pleasure to give you this talk, and I would like to devote the first few minutes to introduce our laboratory, which is the Laboratory of Acoustics and Studio Technologies. So I try to run the presentations. I hope that my screen is shared and you can see it well. Is it working? Everything is okay?
Yes, we see your screen.
Thank you. So our laboratory is concerned with the topics in acoustics and vibration. And our current staff consists of 8 members. The founder of our lab is Philip Augustinovic. He is now Professor Emeritus, so he is retired. And there are 7 active members, 5 teachers at the university with full positions, and also 2 PhD students. And our main activities include education and research, and we also have some industrial projects. I would like to show you a few pictures from our lab. We have a semi-anechoic chamber where we can perform some measurements. Like you see, we measure the sound radiation from a drone in the upper left. We also do some quite interesting musical related measurements. For example, you can see the vibration analysis of a guitar in the bottom left. And we also have a small studio for students to practice recording and audio mixing and so on. And in the next few minutes, I would like to introduce some of our interesting projects just in a few pictures, to get an idea to you what are we working on and what are the main topics. If you come to Budapest, you may see some of our so-called footprints in the city. For example, we were quite active in the design of the new metro line 4. And we have made a lot of measurements in measuring the vibrations of the tunnels in order to calculate what kind of vibration insulation is needed to meet the requirements of sound radiations in the building above the metro line. So the next slide is also related to that. On the top left, you can see a building which is only planned. And my colleague computed the vibration in this building excited by an imaginary metro passing under the building. And on the bottom left, you can see this building built, and this is how it looks now. And similarly, on the right-hand side, you can see vibration analysis of a part of a very large bridge, which is near the university. Little bit different topic or different wavelengths in the topic was the simulation of ultrasonic parking radars, which we did for a company. And the idea is when a new car is designed, they build the sensor into a bumper in some exotic geometrical configurations, which you can see on the top left. And we have created a framework which can calculate the so-called field of view of such a sensor. It consists of a numerical model to tell how the sensor will radiate, how the ultrasound will be reflected from different kinds of objects. And we have made validation measurements for this framework. And in the end, what we get is this so-called field of view where we can see which objects will be detected by a sensor configuration. This is the bumper of the car here, and then we can see which targets are detected by the sensor system. About detection, we also work with detecting UAVs using microphone arrays. We have a so-called acoustic camera system, so a free-form microphone array. Here we have built it into a slab, and then we have a digitizer unit, and we have written our own software to see the camera view of a field, and also what you can see in colors is the acoustic intensity map of a drone is there. You can barely see it, but it is there. So we can track drones using this system in the free field. We are also developing a numerical simulation framework using the boundary element method, BEM. And we have this open source boundary element library developed by my colleague Péter Rucz and myself. And it is an open source framework, and it is a generic tool. You can use it for example, elastostatics, or also you can solve the Helmholtz equations. And it also supports the fast multiple method, for example. Yeah. Another topic by my colleague Gergely Firta is the wave field synthesis or sound field reconstruction, where we want to reproduce the field of a sound source by an arbitrary number of loudspeakers. And Gergely got some very nice generalized theory of sound field synthesis in his PhD thesis. And also one of the main applications which he targeted was the synthesis of moving sound sources. We had two European projects related to aircraft noise. In one, on the left-hand side, we have made a perceptual evaluation of aircraft noise. And on the right-hand side, what you can see is a little bit planning related, where you have an airport, then we want to model what will be the effects of changing the traffic of the airport. And one of the main results was to calculate this awakening indicator metric, which especially related to night disturbance, and it tells what is the probability of waking up due to aircraft noise, mostly in the near field of the airport. You can see the runways of the Budapest airport here in the picture. Yeah, and we have also topics related to musical acoustics. Our PhD student, Dóra Jenei-Kulcsár, is working on the piano model. She has a model of a complete piano consisting of hammers, strings, and right now she is working on the soundboard model using finite element methods. And also she can simulate sound radiation from the piano. And my PhD student is working on aeroacoustics. And this is just one example of simulating the edge tone by means of different aeroacoustic methods. So as you can see, our topics are very wide spread, and we are doing a lot of research and also industrial work. And in my technical talk, I would like to introduce one specific topic, which I worked on recently, and it will be about the nonlinear propagation of sound waves in ducts, also in a musical acoustic application. And I forgot to mention in the beginning, but if you have questions at any time, just please feel free to interrupt me. If I don't notice that you have a question, then just please interrupt, and I will try to answer to make this talk a little bit more interactive. So I will switch to my talk. Yeah, and so this work is concerned with the computational.
Sorry.
Yes.
Nice to meet you. May I have a small question?
Yeah.
The pictures which you showed, which are related to different projects,
Yes.
are they all obtained with your own software, or you also use some commercial software?
yeah, for the building vibration modeling, we also use the commercial software like Nastran and Sysnoise. And what we did for the ultrasonic simulation system, we have used our own boundary element code, but as a validation, we also use the virtual lab software from Siemens because we did it for an industrial partner, and the requirement was that it should also work on an industrial software. And for research purposes, but I will show you, for example, in the talk, we try to implement all the software that is needed. So I will show you in this talk results which from the solvers that we have programmed.
Thank you.
Yeah, okay. So yeah, this topic is concerned with the computational modeling of weakly nonlinear sound propagation. And part of this research was done in cooperation with Juliette Chabassier from INRIA Research Institute in Bordeaux, France. So the topic is very interesting because nonlinear propagation has a lot of industrial applications. For example, there is such thing as ultrasonic focusing. And the interesting thing that nonlinear propagation also occurs in musical instruments. On the top left, you can see the structure of a trumpet. And here is the bell of the trumpet where sound is radiated. And by means of Schlieren imaging, we can capture some photographs of the sound field of a trumpet. And by such an imaging, we can see that at high playing amplitudes, shock waves like the black line here can also propagate inside of the musical instrument. And in this talk, I would like to give an overview of how to model these nonlinear propagation by means of numerical approaches. And I would like to give two examples of modeling approaches, the Kuznetsov equation model and the Menguy-Gilbert model. And I would like to show you the numerical formulations and also the validation and testing of these models. Just to give you an idea of the fundamental phenomena that needs to be modeled in case of nonlinear propagation, in the top left, you can see a so-called seismogram of a wave packet of high amplitude traveling along a simple duct. And we can see this very interesting effect that the so-called wave steepening occurs as we go along the distance. We can see that this initial packet becomes steeper and steeper. And this is an essential result of the speed of sound increasing as the pressure is increased. So the pressure change by the wave itself affects the speed of sound, and then the solution becomes discontinuous and the so-called shock wave is formed. And when the shock wave is formed, then propagating energy, the sound wave is converted into non-propagating energy. And it means that when the wave is reflected from the open end, it will not retain its original form, but we will get a distorted form with a lower energy. Here we can see that after the shock formation, the energy of the wave is decreasing. And then again, when it reached its final form, then we will have a constant energy. And one more interesting thing is that if we take the nonlinear effects of sound propagation into account, and we neglect all the dissipation effects, which are naturally present in any propagation, then we get that shocks develop independent of the magnitude of the wave. It's only a matter of time and propagation distance that a shock wave would be formed. And with this, I would like to introduce the first model, the so-called Kuznetsov wave equation. It just starts from the conservation equations of mass. this is on the top. We have the variables of rho is the density, v is the velocity vector, and then p is the pressure. And the second equation is the conservation of momentum written in a way that takes friction and viscosity into account as well. And the main idea in the Kuznetsov equation is to write the state law connecting pressure and density in the form of a Taylor expansion. And this Taylor expansion is written up to second order. And around the working point of P0, which is the atmospheric pressure, we can expand P in terms of rho up to second order, and we also include the changes of entropy, which will be incorporated into the intrinsic losses part. And if we take perfect gas into account, then we have an adiabatic state law. And then from this state law, we can get the coefficients of A and B in the equation, simply based on the material properties, like the equilibrium density ρ0 and C0 is the propagation speed of sound in the free field. And then making only a single assumption that the velocity field is irrotational, then we can use this phi velocity potential. And of course, the velocity will be the gradient of the potential. And then by keeping all terms up to the second order and dropping all higher order terms, we get a nice nonlinear wave equation for the velocity potential. And this is how it looks like. On the left-hand side, in the first two terms, we can see the linear propagation equation. This is the standard wave equation. And then there are two nonlinear terms appearing. And also, if we consider intrinsic losses, which are generally very small in air at normal frequencies, then we get this second order equation, both space and time. One thing to remark that this is a completely general formulation, which is valid in 1D, 2D, and 3D with the assumption of an irrotational velocity field. And using the expansion of the constitutive equation, this can be generalized into, for example, nonlinear waves in water, which can also be useful in ultrasonic applications for medical purposes and so on. So this is a quite general equation which can be used in many applications, and we will use it for sound propagation inside the musical instrument. To be able to solve the Kuznetsov equation, we turn to a numerical approach, the finite element method. And just as the normal case, we will construct the weak form of the equation. And first, it is useful to introduce a change of variable simply by multiplying the velocity potential phi by the density rho. Then we get that the pressure will be the simple time derivative of this new variable psi. And for this psi variable, we can write the weak form of the equation. On the top, you can see all the linear terms. And in the bottom line, the two nonlinear terms appear. And we can simply write as that the internal so-called forces in the system, depending on the second time derivative, first time derivative, and the variable itself, will be equal to the external forces in the system coming from the boundary conditions forced on the PDA. And the idea is, the idea is to expand this F int on the left-hand side into a Taylor series again, but only of first order Taylor series. And if we have an estimate solution denoted here by the tilde, then we can create a rule for updating or estimate by this delta psi appearing here. And the interesting thing in this formula that we have these derivatives which relate the variable psi and its time derivatives to each other. And these relations can be obtained by prescribing a time-stepping scheme. For example, we can use the Newmark method with the time-stepping parameters to get these derivatives. And in the end, what we get is we get an update method, which will, on a guess, we can calculate this delta psi and update our guess of the solution in each time step iteratively. This is a standard Newton iteration method. And to be able to implement it in a computer framework, we use, of course, some discretization methods. If we, for example, use the Galerkin method using the standard shape functions, then we can see that, for example, the stiffness matrix appearing in this system consists of a linear stiffness matrix part, and we also have a nonlinear stiffness matrix part. And in the generic implementation, what we would need is to update these nonlinear parts because they depend on the actual solution of the system. But we can come up with a more clever solution, exploiting that these nonlinear terms are all quadratic. And by this, when we substitute this psi dot, for example, into the system, we can realize that instead of performing this integral again and again, we only need to store index and value arrays, and by a simple sum, we can compute this nonlinear part. And furthermore, we don't even need to assemble the whole matrix. We can just store the index arrays and perform the matrix vector products on the fly, because these matrices, as general for the finite element method, these are very sparse system matrices. So I think there's enough of theory for this method. I would like to show you a demonstration how this method works in a computer simulation. So I try to open up my simulation framework and just run this example. I hope it will start. Yeah, on the top, so you can see now a simulation running on my computer. And on the top, you can see our main solution variable psi. And in the bottom, you can see that the actual pressure will be the time derivative of this top function in each point. And because we have quite large magnitude, we have around 10 kilopascal magnitude, we can see this wave steepening phenomena occurring here. And this dashed line denotes the approximate position where a shock wave is formed. And we can see that after the shock, the wavefront will be very steep. So we have a discontinuous solution. And then a rarefaction wave comes. And then we have a non-reflective boundary condition on the right-hand side. And then our wave just leaves the domain. And we can also see that when the shock wave is formed, then there is dissipation in the propagating energy, and the magnitude of the wave will decay. Yeah, but even with forcing a harmonic oscillation, we can see that this wave steepening phenomena occurs in the nonlinear propagation. And in the end, this is the number of iterations required for the Newton methods to converge up to a precision of 10 to the minus 10 relative error. So we can see it's quite stable, and a few iterations of maybe 7, 8, 9 iterations is enough in all cases to reach a steady state solution. Of course, if we would increase the magnitude of the pressure wave, the number of iterations required would also increase slightly. Yeah, I would like to go on. This was the Kuznetsov method. And the other method I would like to introduce is the Menguy-Gilbert method. And it uses different assumptions. In the top, you can see the complete equation. What you can notice is that this is not a wave equation. This is a simple advection equation. If you take only the first two terms, this is the simplest linear advection equation. And then we have a nonlinear part where the quadratic term for the velocity u plus and u minus occurs. And then the model can take the variation of the cross-section in the tube into account. And we have a very interesting part on the right-hand side, which is related to the losses at the pipe walls, which occur due to friction and heat exchange with the walls. And of course, as similar to the Kuznetsov equation, the intrinsic losses can also be incorporated. So the main difference is that actually this Menguy-Gilbert model is two equations, one equation for u plus and one equation for u minus. And inside the propagation domain, the two waves are completely independent of each other. They are only connected by reflections occurring at both ends of the tube. And to implement this model in a computer, it is useful to use the one-dimensional finite volume method. And I would also like to talk about how to handle this wall losses term with this exotic fractional derivative appearing here. This is on the next slides, but I would like to call your attention to that this fractional derivative is actually a convolution integral. If we have a function wt, then this derivative is defined as a convolution integral, and unluckily, this convolution is infinite in time. So even if we have a one-dimensional system, we would have to remember the whole time history of the velocity in each position to be able to compute this convolution. And the idea is to mitigate this necessary storage of the time history. And instead of that, we can use auxiliary variables. And I will show you in the next slide how to do that. It is very useful to write the fractional derivative, not in the time domain, but in the frequency domain. This is what electrical engineers like me like to do. So from the time domain, we go to the frequency domain in omega, and we can just see that if we have alpha equals -1/2, as in our case, we just get a simple multiplication of g omega onto the power of alpha in the frequency domain. And this is a nice generic result that this g omega on the power of alpha can be written as an improper integral, which only contains integer powers of g omega. And this is the special case for alpha equals -1/2. And we can approximate these improper integrals by a clever quadrature based on the Gauss-Jacobian quadrature with the weights of mu L and the base points theta L. And then when we have this relation, we get this approximation, and then we can convert our frequency domain solution back to the time domain. And in the end, what we get is that we get a few auxiliary functions denoted here by phi L, and then we get a simple ordinary differential equation for each auxiliary variable. And the nice property is that these auxiliary variables will be local. So their time history won't depend on the space, only on the local time histories of these auxiliary variables. And this approach is used to avoid storing the time history of all the solution and to mitigate the necessity of performing the convolutional integral required by the fractional time derivative. So what this means physically, if we have a musical instrument like a flute or organ pipe or any kind of wind instrument, The wall loss is the main source of loss in the most important range of frequencies. There is also some energy loss due to sound radiation. If we look at the point of view from the resonator, naturally, when we have sound radiation, it is a kind of loss of energy to the resonator. But for most applications, the most important part is in the wall losses. And there are two main effects. Of course, when we have wall losses, then the dissipation will cause decay of the propagating wave. And also a very interesting thing is that because the amount of losses is frequency dependent, we will also have a slight dispersion. This means that inside the duct, the effective speed of sound, denoted here as the phase velocity c, will be frequency dependent. And here is one example. If we have a narrow tube of, I think, 10 millimeters in diameter, then we can see that the effective speed of sound will be lower at lower frequencies. And to follow this behavior, we can use our clever Gauss-Jacobi quadrature and auxiliary functions. And this is how it looks like. We have an analytical formula in the cylindrical tube, which prescribes how the phase velocity should behave. And as an initial guess, if we use the standard Gauss-Jacobi quadrature, we get a result which oscillates around this analytical solution. So we can further do some nonlinear optimization to tune the quadrature base points and weights in order to match this analytical solution in the audible frequency range, which is 20 Hz to 20 kHz. And on the right-hand side, we can see that if we increase the base points of the quadrature, then we can get a little bit lower error rates. But after a while, like after L equals 8 or 10, it is not useful anymore. We don't get very much better results. So for example, L equals 8 is a good choice for the simulations to include the effect of wall losses. Yeah, and this is what I would like to show you in the next demonstration. What happens if we simulate this behavior, and how does it look in the time domain? So I try to run this demo. And yeah, you can see velocity wave coming from the left. It is a wave packet, and then it will be reflected from the open end on the right. And you can already see that this tail of the function appearing here, and also the magnitude is slowly decreasing. These are the two effects of the wall losses. Of course, the decay, and we can explore it here, that we have the decaying magnitude and also the dispersion effect. I see that we have a question, so please.
Yeah. I have a short question. So what
Yes.
The dispersion of losses at the wall.
Yeah.
So what is the origin of it? So is there maybe I missed at the beginning of the seminar. I'm very sorry about this. Yeah, but this.
Yeah, I think.
What is the reason for the dispersion loss?
Yeah, I haven't explained this in detail, but there are two things which cause the decay. So if you consider fluid flow in a pipe, you notice that there is the flow velocity must be 0 at the walls because the fluid sticks to the wall. Yeah, and the same effect you have when you have an acoustic wave. You have small movement of the particles, but near the wall, the fluid must stick to the wall. So you have this so-called boundary layer developing at the wall, and there is a lot of friction in this boundary layer. And this is one part of the loss. And you have a similar effect of heat exchange with the wall. We usually suppose that the wall of the instrument has a constant temperature. But if you have an acoustic wave, then inside the wave, you have adiabatic propagation is supposed, which means the temperature is not constant. So therefore, in order to satisfy these conditions, then you must have some heat exchange with the walls. So these are the two sources of loss occurring in a duct, and these sources are inversely proportional to the diameter. So if you have a very small diameter, you have a large amount of wall losses. And if you have a large diameter tube, the effect of this wall losses is smaller.
And then they give this 1 over square root of frequency dependence. Am I right?
Yes. This 1 over square root of frequency dependence is actually a so-called high frequency approximation. This is very close to the true result, which contains some Bessel functions and so on. But in the normal range of frequencies, like in the audible range, we are very, very, very close to that.
So when does it break?
When the assumptions break. So
yeah, at low, so as I understand, at low frequency it should break, right?
Yes, at low frequencies, for example, if you have like 1 centimeter diameter pipe, then under 10 hertz you cannot use this approximation. You can for a given frequency you can calculate the boundary layer thickness. And when the thickness of the boundary layer is close to the radius of the tube, then the approximation breaks.
I see.
So that's the basic idea. And yeah, it is possible to calculate these layer thicknesses. In the normal range, we have around 100 micrometers, and so on. Around that is the range. Yeah.
Thank you. I see there's another question from Sergey.
Yeah, please.
Yep, so probably I missed that, but you told that the amplitudes, like plus and minus, they are dependent only on the boundaries, but not during the propagation. So I do not clearly understand why is it so. So why they are independent?
Yeah, this is the one supposition of this Menguy-Gilbert model. And they had to do this to be able to separate the positive direction propagation and negative direction propagation. It is only a supposition of the Menguy-Gilbert model. And in the Kuznetsov equation, we do not do this. And I will show you in a few slides what are the consequences of supposing independent waves. So this is not generally true. It is only a simplification applied in this model. So it neglects the effect of the other wave on the one wave.
Yeah, thank you.
So yeah, it's supposition of the model. Yeah. Okay, I think I will go on. So we have discussed the effects of wall losses, and now I would like to give a short analysis as a comparison of the two models. And let's just repeat that in the Kuznetsov equation, we have solved it numerically using the finite element method. And this is a second order equation. And the Menguy-Gilbert model is solved by means of the finite volume method. So we can expect that the two numerical solutions will have different behavior. And this is what is shown on the top right. I have took this wave packet example and performed time domain simulation using different resolutions in space. And we can see as we decrease the resolution to smaller and smaller numbers, we will of course deviate from the analytical solution. yeah, this is just linear propagation. So we have an analytical solution. I forgot to mention that in the beginning. And in the Menguy-Gilbert model, we can see that the wave packet preserves its shape. So there is no dispersion in the solution, but we have a decaying magnitude if we decrease the resolution. So we have large numerical dissipation. On the other hand, if we look at the Kuznetsov equation and the finite element strategy, we can see that the magnitude is preserved even at low resolutions, but we have large dispersion in the model. So the shape of the wave packet will be distorted. So these are two different behaviors related to the numerical nature of the solution. And we can also explore the convergence rate of the two models. If we increase or decrease the element size, we can expect for the finite element model to have a second order convergence. This is the blue one. And from the Menguy-Gilbert model, the convergence rate must be between 1 and 2. And that is because we have to use this flux limiter approach, which will do an interpolation between a second order and first order scheme based on the actual local space derivatives of the solution. Yeah, and this is very well retained by our numerical solution. So the interesting thing to simulate is the shock wave, as I have shown you in the first example. And if we have a harmonic forcing with a magnitude of velocity capital U, then, then we can calculate this shock formation distance sigma. And here in the top diagram, I have compared the two methods, the Menguy-Gilbert solution and the finite elements solution of the same problem. And we can see that they actually give very well similar solutions in this problem. They both reproduce the formation of the shock wave, both reproduces the decay of the magnitude after the shock wave formation. And on the bottom left, we can see an analytical solution which is only valid before the shock formation. This is the so-called Fubini solution of the problem. We can only compute it in case of harmonic forcing. So, and we can see that this reproduces this wave steepening effect. And also our solutions give very good agreement to this Fubini solution. Maybe it is worth mentioning that in order to have well-behaved numerical solutions, we must take some considerations. For example, in the finite volume solution of the Menguy-Gilbert model, we have to use the flux limiter scheme. And if we turn this flux limiting on, then we can see, if we turn the flux limiting off, then we can see that near the shock wave, we get these additional artifact peaks, which are not supposed to be in our solution. And the similar phenomenon in the finite element solution, in the time stepping scheme, we have to include a dissipation parameter defined by this alpha h. And if this dissipation parameter is too small, or there is no dissipation at all, then at the very steep variations of the pressure, we will see these oscillations, which are, of course, numerical artifacts of the method. And finally, on the right-hand side, we can also see that if we decrease the resolution of the finite element method, this will also increase the dissipation of the scheme. So in order to retain accuracy, we have to be, of course, careful with the resolution. Yeah, and now a short slide about the differences between the two models. There was a question about this, that why are the two waves are independent of each other. And this is only in the case of the Menguy-Gilbert model. And here is one demonstration which shows the difference if we have a high magnitude shock wave propagating in the tube and then reflected at the open end. We can see that the two methods will give different solution after the reflection. And in this region, which I marked in the diagram, we can notice that there is a little bit of shift between the two solutions and at one time instance. And that is because in the Menguy-Gilbert model, the local change of speed of sound caused by the other wave is not taken into account in the solution. So this is one difference which we can observe if we simulate high magnitude shock waves. Yeah, near the end, I would like to say a few words about the implementation of the models and how to have an efficient implementation of these equations. In the right-hand side, you see a comparison of different implementations of the finite element method, and also the finite volume is there as a reference. And there are a few techniques which we can exploit to make the implementation efficient. So if we do the full assembly and do the full Newton iteration as written in the book, we will get the top result. And we can see that actually assembling the system matrices requires a lot of time, because we have to do that because of the nonlinear nature, we have to do that in each iteration. So this is the full Newton official method as written in the book. If we switch to the initial Newton method, which only recomputes the nonlinear part once for each time step, and not in each Newton iteration for each time step, then we can almost halve the computational cost. And the most work is spared in the assembly step. We can see that the blue assembly step is very much reduced if we use this initial Newton method. Another idea is to lump the system matrix of the used in the finite element method. Lumping means that we concentrate the elements to the diagonal of the matrix, and that's why we can see that the solution step, denoted by the yellow part, will be much smaller in this case. But on the other hand, it will take more iterations to compute the solutions, which is denoted by this red marker. And one thing I mentioned in the beginning is that we do not need to assemble these nonlinear matrices at all. If we only store the coefficients and perform the matrix vector product on the fly, then we can spare the whole blue assembly part. And that's why this lumped solution is much faster. But we can see that because of the lumping, we spare some of the solution time, but the matrix vector product times, denoted by the red here, are increased by a lot. And the best result which we got is to use the initial Newton method. So don't update the nonlinear part in each iteration. Do not use matrix lumping, but use the fast matrix vector product. And in this case, we have reduced the computational time to around, I don't know, 1 to the 10 or like this in case of this final solution. And still it is not fully optimized. Some of the iterations are, or the main part is written in MATLAB. Only the fast matrix vector product was implemented in C++ to gain some computational time. And if you compare this to the finite volume method, which is limited course, to the one-dimensional case, then we can see that the computational times are similar to those. The most of the time is required by computing the flux terms in case of the Menguy-Gilbert model. Yeah, and some thoughts about what are the current limitations and capabilities of the two models. In the Menguy-Gilbert model, we can incorporate the effect of wall losses, which is very important for musical instruments. But because the model is limited to one dimension, it has a term that takes variation of the cross-section into account. However, it relies on a plane wave approximation, which won't be valid if we have a trumpet like this, for example. And here is one result. Here we can see the frequency-dependent input impedance function of a simplified brass instrument, which is just an exponential horn. And in the linear regime, we can compute this impedance function using a one-dimensional transmission matrix model. And if we compare it to the Menguy-Gilbert, we can see that because of the change of the cross-section, here we have some serious deviations from the correct solutions. In contrast, in case of the finite element model, the problematic part is the inclusion of the wall losses. This can be done, but only in the linear regime. So if we do this, then this is for this trumpet geometry, which you can see here. We can get a very nice impedance curve, but then we have troubles when we have to simulate the nonlinear propagation. And I would like to show you one example of the sounds produced by such models. So in order to have a trumpet-like sound, we need one more component, and this is the excitation mechanism of the player. So we will have the buzzing lips, which is a simple damped mass spring oscillator system. And the importance of the lips in our model is that it will modulate the flow going into the acoustical resonator. And when actually a trumpet player is playing the trumpet, the two main control parameters that he has on the sound is the muscle stiffness of mainly the upper lip, by which he can control the resonance frequency of the mouth, and of course he can play at different blowing pressures. And in the end, if the right muscle stiffness and blowing pressure is found, a self-sustained oscillation is produced, and we can have a steady state sound. And let's just compare two sound examples computed by the Menguy-Gilbert model, one with the linear propagation model, and in the second case we have a nonlinear propagation. And in both cases, the player starts at 8 kilopascal blowing pressure, and then the pressure is reduced to 2 kilopascals in time. I try to switch to the sounds. So first we will hear the linear effect. You can hear as the pressure changes, also the timbre of the sound changes. Let's play it once more. Can you hear it? Sorry.
Yes, yes, we can hear it.
Yeah, okay. So once more the linear example. Yeah, we can hear the decay. And in the nonlinear case, what you can hear, especially at the very beginning, if you try to focus on that, I will show it once more. You can hear this typical brassy effect in the very beginning. Of course, it doesn't sound like real trumpet, but it can reproduce this brassiness observed in the sound of brass musical instruments. So this also shows that the modeling of nonlinear sound propagation is very important in the case of such brass instruments. And yeah, this we can also see, of course, in the waveforms that the two linear and nonlinear propagations will give similar frequencies in the spectrum, but the timbre of the sound color will be very different in the two cases. And yeah, this brings me to the conclusions of this talk. So this was concerned with the nonlinear sound propagation in music instruments. And we have discussed two different numerical models for that. One was the Kuznetsov equation, and the other is the Menguy-Gilbert model. And they were solved by different numerical strategies. We had a nonlinear FEM, and for the Menguy-Gilbert, we have used the finite volume method. And we can see that both approaches are capable of solving or simulating this spectral enrichment or the brassiness of the sound, and they capture shock wave propagation quite well. And for the future plans to extend this work, a nice thing would be to extend this finite element solution to treat also the Wall losses in case of the nonlinear model, but this seems to be quite challenging. And there is a new approach called the energy quadratization approach, which appeared recently and is solved in nonlinear dynamic systems. And it gives an improvement on the iteration times required for solving the Newton iterations. And with this, I would like to thank you for your kind attention, and thank you for organizing this seminar. And of course, if you have more questions, please feel free to ask. I'm happy to discuss. And thank you very much. In the end, I have some references. Yeah, thank you.
Thank you, Peter. We have one more question from Sergey.
Yeah.
And Mikhail.
Yeah.
Yes, so I was wondering about, again, the limitation of the method, because, again, as far as I understand, this is all for weak nonlinearity. And I mean, I wonder what will happen if we'll start to increase the nonlinearity. And basically, will we have some instabilities related to the nonlinearity? So like modulation stability, or we will not reach these effects for the considered cases. So
yes, thank you. So for the musical instrument application, this weak nonlinear simulation, which considers the terms up to second order, is surely enough. In the musical instruments, you know, we have air at normal conditions, like 100 kilopascal static pressure, and the maximum magnitude, which occurs, for example, in a trombone or a bass trombone, where you play a very fortissimo sound, it's around 20 kilopascals. So these models will still work. If we increase the magnitudes further to have, I don't know, like sonic booms and such kind of effects, then you would need another model, because with this model, you still have this Taylor expansion in the very beginning. So they have a limitation regarding the magnitude. So you cannot approach this 100 kilopascal or the normal pressure limit. Yeah. But I haven't tried to do simulations at such high magnitudes. Of course, the solution will deviate from from the physical behavior because of the approximations are also limited. If we increase the magnitude, we also need higher numerical dissipation in the schemes, so they will also deviate. So yeah, if you have high magnitude, then that can be a problem, that you have numerical instability as well.
Thank you.
Mikhail, questions from you?
Yes. Hello, I'm sorry, Mikhail's computer unexpectedly shut it down, so I will replace him. So the question was, well, in the very end, you have demonstrated this trumped sound, and do you have any comparison with the experimental data?
Not yet. So the main difference between this simulation and the real trumpet is now the geometry. So this is only a straight duct with a similar length to a trumpet. So I haven't compared the sound spectra of real instruments yet. Previously, we have done some simulations on the playing frequency of the instrument, depending on which key you play, for example, so which valve you open for the trumpet and so on, and those were good agreement in relating to frequency, and also we have tested because when you play at large magnitudes, another effect occurs with the lips, that in some portion of the period, the lips will close completely, and then it is not a normal oscillator anymore, because you have nonlinear effects there as well. So you have to be a little bit careful about this. But yeah, it seems possible, and definitely a next step would be to have a realistic trumpet geometry, a realistic model of the excitation, and then compare to experiments. But this is yet to be done. This was just an example showing the importance of the nonlinear effect.
Yeah, thank you. Thank you very much.
Thanks a lot.
Any other questions? If there are no questions, then
Maybe, sorry,
okay. Sergey,
one more question. So it was about convergence. You were talking about, again, limitations of the method. Probably it was slide number 10. And it was shown that the relative error rises kind of after somewhat 20 kilohertz.
Yeah.
Yeah, so this is because we are moving out of the assumption of the method, or
Yes,
for
so
other reasons.
What you can see here is in this case, this initial quadrature, which produces this fluctuating curve, has to be optimized by tuning the weights and base points a little bit. And by optimization, we get closer to the analytical curve, but only in a domain which we can select. We can, of course, select larger domain. We can go up to 50 kilohertz as well, but then we are in ultrasound and cannot hear anymore. So theoretically, it is possible to change the range of the optimization, and then we can get maybe a little bit higher error, but in a broader range. But as those are outside of the audible range, I didn't see I didn't see it meaningful to do it in this application, but it would be possible. And one more thing, because we were talking a little bit about ultrasonic applications. When you go to the ultrasound regime and you have high magnitudes, there is one more thing to consider, that in ultrasound, the intrinsic losses will increase. And actually, after a while, these intrinsic losses will be dominant over the wall losses. So we experienced it with the ultrasonic parking radar system, that how far your parking radars sees is dependent on the attenuation of the free field propagation, and it depends on a lot of factors in the ultrasound regime. For example, you get very different dissipations if you change the humidity there. Yeah. So yeah, this is a limitation. Going back to your original question, this is a limitation of this quadrature optimization approach, but you can, of course, choose your limits to your need.
Yeah, thank you very much. Probably one more question from me.
Yes.
So, since these are all your developments, actually, are they open source, or you kind of developed them for yourself or for some companies?
Yeah, these were so-called just for fun. So I haven't published these sources. The finite volume strategy was published in another paper. This Benjamin paper discusses the finite volume solution. So the theoretical steps are there. I just try to understand it and do my own implementation of that. So yeah, these are not shared yet, but if you want to have it or try it out, I am happy to share with you.
Yeah, thank you, and thank you for the talk. Pretty nice.
Yeah, thank you very much.
Thank you.
Any other questions? If no, then we can continue with the presentation about our project.
Yes, I will stop sharing that. And
Okay, then Sergey, please share the screen.
Yep, so yes, just a second. Yeah, do you see the screen?
yes.
Right, so this is just a brief introduction of our laboratory. So this laboratory was established just a couple of years ago. It's based, developed from the Department of Physics at Menguy University, and we are quite young, so we have lots of students who do work. So we try to work in different areas of acoustics, so including some fundamental phenomena like high quality factor resonance states, topological acoustics, but we also look into some particular practical applications like noise control, especially using metamaterials, some acousto-optical and acousto-electronical systems, sensors, maybe microfluidic devices, and as well some medical acoustics. Yeah, for example, wireless power transfer. Yeah, in order to charge various medical implanted devices. And probably we have a better picture for now because our laboratory is constantly growing, and we have a tradition to move our equipment from one room to another because we increase the number of our facilities. But one of the main setups for which we which we use to obtain results is this chamber, which was developed by well, our employees, our students and PhD students. So it just represent a two-dimensional anechoic chamber, which can work basically in two regimes. So it can be a chamber, but it can be a waveguide with straight walls. So basically, we can test well, almost any two-dimensional system there. So it might be periodic in one direction, or it might be a finite size. Well, we also develop some impedance tubes, as well as setups for measurements in water. Yeah, and we have some different measuring equipments. So basically, these are mostly microphones, a couple of analyzers, and etc. Yep. And regarding the particular projects, so what we study, so historically, first of all, these are metamaterials, maybe because historically the whole department was developed from the laboratory of metamaterials. Yeah, so this is one of our main topics in general, not only in acoustics, but in radio physics and in optics as well. So these are just some examples of what we were doing. For instance, these metamaterials for noise insulation, like chambers, which can be ventilated and, well, basically optically transparent, but still block noise. And they are based on coupled Helmholtz resonators. So this coupling is required in order to increase the frequency range within which we achieve the noise insulation. Yep, and we kind of try to develop these ideas further in order to develop absorbing metastructures and other structures to control noise using subwavelength layers, actually. And another kind of branch of the development of metastructures are lenses. So how to use metamaterials in order to focus ultrasound in water, yeah, specifically for human body. The initial purpose was to, again, for power transfer systems, but in general, now we also switch to systems for manipulation, like acoustic tweezers, yeah, how we can control particles, how we can move them using metamaterials and acoustic forces. So I'll give a bit more details later. And of course, we work in some other systems just to demonstrate a couple of more specific results. So for instance, we have this metapanel structure. So it consists of Helmholtz resonators, which are connected through this channel with high thermoviscous losses, because this channel is really narrow and the thickness of the whole structure is just 12 centimeters. But we numerically demonstrated, well, we are not experienced in our own methods, so we used COMSOL multiphysics, but we demonstrated that the absorption can be about 10 hertz, which is, well, pretty nice. So the structure is really sub-wavelengths. And I believe that we also have some preliminary measurements which kind of supported these results in the similar system. And for instance, yeah, regarding the noise insulation, we have quite recent work dedicated to metamaterials based on, well, not really based, but inspired by sonic black holes. So sonic black holes are these nice structures in which the speed of sound decreases with coordinate, yeah, with propagation, ideally till 0. And we decided that we can kind of use these structures in order to control noise in ventilation channels, because such structures probably can block noise but still allow the airflow propagation. Yeah, so these are measurements for kind of real life conditions when we have a fan generating both noise, acoustic noise, and airflow. Well, there is no graph demonstrating how the airflow behaves after the structure, but for exactly this particular transmission coefficient spectra, the speed of the airflow is suppressed just by 25%. So we kind of achieve experimentally both suppression of sound and still pretty good ventilation properties. But regarding the other projects which are not related to metamaterials and noise, we try to work on various medical applications and particular processing of medical signals, for instance, like lung sounds and phonocardiograms of heart, combined with processing of electrocardiograms and various other signals which you can register from human body. Yep, and we implement different methods, which are mostly based on time frequency analysis. So how to determine which signal corresponds to some disease. Yeah, so which signal indicates whether a person needs more specific treatment or not. This is a kind of a long-going project, so we do it for several years, I guess, and we plan to do it for several years more because we gather statistics. Yeah, so this is kind of medical application, so that's why we need to gather lots of data. We have some support from medical universities, actually, and physicians who directly work in this field, for instance, in the field of lung diseases. Yep, and we actually developed a prototype of the system which allows us to provide the screening diagnostics of lung system of human. But, well, this work is still in process. Just to mention, we try to use not machine learning, which is quite popular nowadays, but we try to kind of more rely on time frequency analysis. But we still use machine learning in order to find some statistical dependencies. All right. And regarding more fundamental things, we are quite experienced in resonant physics, yes, so mostly resonant photonics. And in terms of acoustics, we consider different high quality factor states, basically bound states in the continuum. So these are the states which are, well, in simple words, they are formed by interference of several leaky modes of the system in such a way that the radiation channels are closed. Yep, and in a theoretical limit, in ideal case, the quality factor of such a state is infinite. Yeah, because the state is not coupled to the far field. Yeah, so there is no radiation. But of course, this is just a theoretical thing. And several works dedicated to these states. For instance, our colleagues, they demonstrated numerically demonstrated the excitation of such transverse modes inside of solid resonator. So this is just a solid sphere which is surrounded by air, and it can be shown that basically inside such a resonator we can have this kind of transverse mode which is completely decoupled from the outer space. So you cannot just excite it from the far field and it will not radiate in the far field. Yep. for another works, again, we have these structures based on coupled Helmholtz resonators, and we have a study on the resonance states of these Helmholtz resonators, so how we can control the coupling of these resonators using simple tools, simple adjustments, and we demonstrated both again numerically and experimentally that, well, and actually theoretically, that we can excite fancy states, like again this bound states in the continuum, or probably achieve, for instance, exceptional points when we break the linear independence of our modes of the system. Yeah, so these are just some of the results. Again, so I'm talking about these states with high quality factor, which are antisymmetric states. Yep, you can see at the this field distribution of the eigenmode that the field is localized, well, mostly inside the resonators. And we've done the measurements using this two-dimensional anechoic chamber, so we can achieve rather large, well, not extremely high, I would say, but still quite reasonable quality factor. And we also can measure, for instance, the phase difference of the fields inside the resonators, just to demonstrate that we indeed have this antisymmetric mode. All right, and well, the main purpose of this resonance states is, of course, just to find how they will affect some practical systems. So what are, how we can use them. And for instance, if we consider the absorption spectra, we can demonstrate that excitation of such states actually result in the increase of absorption coefficient. And if we modify our system a little bit just by introducing porous insert made of some porous material, we can break a little bit, break the inversion symmetry, meaning that, well, for wave propagating in one direction, we will have one absorption coefficient, but for the wave propagating in a different direction, we will have a bit different absorption coefficient. So again, we measured it experimentally. The difference so far is not really large, I would say. So, well, you can see it, but we believe that results can be improved, of course. But in general, we try to develop the means how to control states, local states of unit cells of metamaterials in order to develop some complicated systems. All right. And other works, which are again dedicated mostly to, I would say, more to some fundamental effects, which are happening in acoustics and basically in other systems as well. I would say some kind of universal phenomena. For instance, we consider various meta-atoms for which we can control scattering properties. Yep. So, for instance, exactly in this system, we know that we can have monopolar scattering type and dipolar scattering type, all these mirror resonances, and we can combine them in such a way that we can control the directivity of scattering. Yep, and for instance, achieve like Kerker or anti-Kerker effect, meaning that we have just like forward scattering or backward scattering. Yep, and we can modify these meta-atoms in order to like find regimes where we combine different multipolar resonances to achieve some specific scattering patterns. Yep, and regarding the scattering, again, another types of works, they are dedicated to the acoustic forces. Yeah, so how we, for instance, can manipulate particles using acoustic fields. And for instance, again, so if we consider various particles of, for instance, this kind of elliptical shapes, we can demonstrate that depending on the orientation of this particle, depending on its size and shape, well, the force acting on this particle will move it towards different directions. And again, these forces, they are associated with the kinds of resonances which we excite with these particles. And for instance, if you consider some specific practical applications, yeah, like here on the right figure, we can say that, for instance, if you have particles of different shapes, like in blood, we have these red cells, which are kind of elliptical ones, and we have the white one, which are spherical ones. So, and depending on their shapes, the force acting on these particles, I mean the force from acoustic field, it will just separate them because, well, elliptical particles will move upward or downward, but the spherical one, they will just continue traveling in the same direction, right? Yep, and probably the last slide is, again, well, our colleagues also develop methods for computation. So in particular, well, I'm not really expert in this particular project, but I believe there are colleagues who can comment more on this thing. But as far as I understand, the general idea is to develop transformatic methods in order to again analyze scattering and probably absorption of ensembles of particles. Yep, so how we can describe the ensembles of spherical particles in terms of, again, their multipolar resonances. Yeah, so how we can look not at some specific particle, but the interaction between them, like binding, or probably some other coupling effects. Yep, so I guess this is more or less the general introduction to our laboratory. Yeah, please ask questions if you have them.
Thank you. It was very interesting, and it seems to me that you are doing a lot of fundamental research. Or is it also related to industry? Maybe that human sensing project is some kind of
Yes, so we have some contacts with industrial partners. Again, mostly this is about these noise insulation structures, because, well, their application is straightforward. So, but and for other things, I believe that, well, we have some contacts with laboratories which are interested in microfluidic devices and biosensors, and, well, acoustic biosensors in particular. But well, mostly we do kind of fundamental science, and we are not really experienced in kind of interaction with industry. Yeah, I would say. But we are just at the beginning of our path, I would say.
Thank you. It was very interesting, and yeah, all these topics. I try to understand a little bit of it, but yeah, it seems that you are doing really high quality research. So thank you for the presentation.
Yeah, thank you. Well, we hope that we did do nice things, but if you have some more questions regarding any project, I can say more words about them, or our colleagues can add something. Maybe I forgot some interesting project, I don't know. So please let me know. Yeah.
Yeah, I think that there are no questions. There were no questions from the audience.
Well, it would be strange if, for instance, our colleagues will ask questions about
colleagues
their
are
own
here.
projects.
Yeah, maybe I have one more question. In this slide, I see that you have a master program. Can you please tell me a little bit about this? Just sorry, just I wanted to say that we also take part in the master program at Budapest University, and we are at the electrical engineering faculty. But yeah, at this time we don't have too much students. Like we have maybe 7-10 students in each semester. How is it on your side?
Yep. So this is not the exact what we have now. So this is the goal for 2030.
Okay.
Yep. We are developing the master program. So we actually write the how's it called? Not textbooks, but we prepare materials for students. Mostly what we have now for educational purposes, these are projects. Yep, so semester projects in which students are involved. So they kind of try to do all parts of the research, starting from numerical simulations, theoretical calculations, yep, and some experimental things. And usually, I would say that each year we have, I don't know, like from 5 to 10 students who work on this project. Well, but for now, we do not have an established program exactly for acoustics. That's our hopes, I would say.
And you expect physics students there or engineering students?
Mostly physics students, because, well, again, there is a department of physics. We have different tracks. So we have numerical tracks where people concentrate on studying and development of numerical methods. I guess, well, Alexei is not here anymore, but Alexei Sherbakov, so he was the head of the master program dedicated to exactly the numerical methods. Oh, I closed the presentation, sorry. But yep, so we are concentrated on fundamental physical effects.
Yeah, okay, thank you.
Yeah.
I think that if there are no questions and comments, then we can finish for today. Thank you, Peter, for your presentation. Thank you, Sergey.
Yeah, so thank you very much. Yeah, it was nice to meet you, nice to listen to your talk, and again, the general talk about the laboratory. Yeah, well, I have hopes that probably we can find some joint interests and probably we'll do something together someday. So that would be nice.
Yeah, it will be very nice. And also very much thank you from my side to Maria for organizing this, and also to the whole laboratory for inviting me to do this talk. And it was a pleasure. Thank you for the lot of questions. And yeah, I wish you all the best, and also hope to visit St. Petersburg sometimes. Yeah.
But in summer, I would say.
Yeah. Yeah.
Yeah, definitely. Thank you, Peter.
Yeah, thank you. Thank you very much.
Bye.
Thank you and goodbye.
Goodbye.